when we solve problems in science and engineering, we use real numbers pretty much all the time without even thinking about it too much. But in fact, the real number set is a bit odd in some ways. So, for instance, the real numbers are infinite in two senses. So, first of all, they're infinite in the sense that they get infinitely large, right? There's no upper bound or no lower bound on the real numbers. But they're also infinitely divisible. So, between any two real numbers lie infinitely more real numbers. Well, if we're going to have a computer that has a finite amount of space and we want it to get answers in a finite amount of time, we can't exactly reproduce something that's infinite. So somehow we have to make a compromise. And computing more or less splits up into two major categories based on which choice you make at this stage. So in symbolic computing, that's with packages like Maple, Mathematica, and many others. They do numerical computations too, but their emphasis is on symbolic computation. In those systems, a number like the square root of 2 is simply a solution to the equation x squared minus 2 equals 0. And you can express it to as many digits as you like, but the more digits you want, the more time it's going to take. And in fact, any given computation takes a finite amount of time, but there's no upper bound on the amount of time it takes to solve a particular problem using symbolic computation. For the most part, in scientific and engineering applications, we tend to stick with numerical computation. And there, what we do is we give up the exact representation. So we don't represent the square root of 2 exactly. Instead, we say it's equal to 1.414 ... to some number of significant digits. But we stop at some point and call it a day. And so that means we use a finite set to substitute for the infinite set of real numbers. And that has some interesting consequences. So let's talk about that set. So the floating point set of numbers has, first of all, we can build it in two stages. So you start with 2 to the m equally spaced values in a standard interval between 1 and 2. So 1 would be a floating point value, and then we go up to 2, but not including 2 to the m times. So on a real computer, most computing these days is done in what's known as the IEEE 754 standard, or what we tend to call double precision. That term is a little bit tricky in some programming languages, what exactly that means. Regardless, these days it's the standard thing to do. Almost all applications will use double precision by default. In real double precision, m would be 52. You'd get 2 to the 52 values between 1 and 2. Here you're seeing it for m is a much smaller number. I think it's about 16, or m is equal to 4, I believe. So you're just seeing 16 equally spaced values between 1 and 2. Okay, and then in order to get the rest of the real, in order to get the rest of the floating point set, we take those numbers and we scale them and move them to other intervals. So in other words, double these numbers and then they would live inside the interval between 2 to 4. Double them again and move them to the interval 4 to 8, and so on forever, in principle. And then you could also take this standard interval, multiply it by a half, okay, so squeeze them together, and then move that copy into 1/2 1, multiply that copy by a half again, and move it over, and so on. And so you get a set that looks something like this. So as you move to the right, the space between numbers is not equal. Okay, it starts to grow. As you move to the left and get closer to 0, the space between the numbers tends to shrink. Now, in reality, this process has to stop after a finite number of copies too. In double precision, we have 2,048 copies for the positive floating point numbers. But we're not even going to worry about that. So if you got a result that was bigger than the biggest floating point number, that's called overflow in this direction. If you got a number which was smaller than the smallest positive floating point number, that's called underflow. It is a real problem in some computations, but we're just not going to deal with it. We're just going to take it for granted. We're going to more or less assume that we could go out as far as we like anytime. So another way of getting your head around these numbers is to graph the distributions. So here's one graph where I'm showing how many values are less than or equal to x, where x is on the x-axis. So you can see that here's our standard interval, x between 1 and 2. Okay, within there you have equally spaced points. And from 2 to 4 you have equally spaced points. And from 4 to 8 you have equally spaced points. But that spacing changes as you go from left to right, so the overall trend is nonlinear. On the other hand, if we just look at these numbers differently, if we take a log scale on the x-axis, okay, well, that means that the points within an interval are nonlinearly spaced on this scale, because in reality they're linearly spaced on the linear scale. But if you look at what happens to their overall trend, that's linear on this scale, because the original set of points is distributed uniformly, but then they're scaled geometrically as we go larger and smaller numbers. The difference between 1 and the next number is called machine epsilon or machine round-off. And we'll give it the symbol epsilon sub m. That's a built-in value in MATLAB called eps, and you can see it's 2.22 times 10 to the minus 16th, which is actually 2 to the negative 52 power, coming from that fact that we have 52 values, 2 to the 52 values between 1 and 2. So that means that if we start with the value 1, and MATLAB shows that it's exactly 1 here, if we add eps to it, we get a number which is different from 1. And then if we subtract 1 again, we get the accurate result, eps once more. On the other hand, if you take 1 and try to add a smaller number, then the answer is still exactly 1. There is no floating point number there, and so we just stay at 1. Now that's not the same thing as saying epsilon is the smallest number. That's not true. It's only the smallest number that you can represent relative to the scale of 1. So you have to get the idea of relative accuracy as opposed to absolute accuracy in floating point. So we can represent the number 10 to the minus 50 just fine. In fact, we can go down to as small as 10 to the minus 300 or so. But if you add that number to 1, it has no effect. It's a lot like significant digits in science. So here's a more formal mathematical statement. The floating point representation of x, which we represent as this function FL of x, is some number which is close to x in a relative sense. Okay? So one way of looking at this value is if we take 1 plus epsilon times x, that's the floating point value of x, minus x itself. Divide that relative to x. Well, if we simplify that, you see you get epsilon. So epsilon really does mean the relative change, or the relative perturbation that we introduce in order to turn x into a floating point value. And what we can say is that epsilon is guaranteed to be no larger than machine epsilon. So because machine epsilon is about 2 times 10 to the minus 16th, another way of writing this is that if you look at the difference between the floating point value and x itself in relative error, take the log of both sides, right? We know that this is epsilon. Well, in base 10, it's about minus 16. In other words, you have about 16 significant digits. Which is a lot. You know, most of the time in engineering, you're lucky if you have 2 or 3. And that's true in many of the sciences as well. So MATLAB represents all numbers this way by default, unless you tell it otherwise, even though you may not see all those digits all the time. So for example, and this display is controlled by a command in MATLAB called format. So the default is what's known as format short. It has a built-in value of pi, and it will only show you 5 significant figures. However, there really are more there, and you can see them all by asking to see things in format long. And here you see that there are 16, more or less, significant digits. Okay, those 16 significant digits are always carried along even when they're not displayed. And what that means is that if you take the result of a calculation that's displayed in short format, and you only take those 5 significant digits and then you do something else with it, you've just thrown away 11 significant digits, which is generally a bad idea. So you never want to prematurely round off your result in the middle of a computation. And you can do that if you forget that MATLAB actually has all those digits available to you.